The topic of this lecture is definition of Riemann integration. We'll cover these points in this lecture: definition of MFI, small mfi, WFI, subdivision, component intervals, lower and upper sum, example, lower and upper integral, example of characteristic function, and Riemann integration. So let us see the first definition. It says that if I be a bounded interval of real numbers and f is bounded real valued function defined on I. That is, I is bounded interval and f is bounded real function defined on I. Then we define this capital MFI by supremum value of fx where x lies in this interval I. Small mfi is infimum value of fx when x lies in this interval, and wfi is capital MFI minus small mfi. So let us understand these terms by an example. Let fx is equal to x square where xi is interval 0 to 3. Then capital MFI, that is the supreme value of fx when x lies in this interval, is given by f at 3. That is 3 square, which is equal to 9. Why this is so? Because fx is equal to x square is increasing function between 0 and 3. So the maximum value will be obtained at 3. Similarly, the small mfi, that is the infimum value, that will be obtained at f0, and its value will be, according to this definition, will be 0 square, that is 0. Then the wfi, which is the value of this minus this, will be 9 minus 0, so it is equal to 9. Now let us see the definition of subdivision. By subdivision sigma of closed and bounded interval AB, we mean a finite subset sigma which contain x0, x1, x2 up to xn of AB such that A is equal to x0, this is the first point, and xn is equal to B, last point, and all these points lies between this, and strictly follow this inequality that x0 is less than x1, x1 is less than x2, x2 is less than x3, and so on. Let us see some example. Let AB is equal to close interval 0, 1, then 0, 1 by 4, 1 by 2, 3 by 4, and 1 is subdivision of AB, because by definition it is containing finite points and follow the inequality that 0, then 1 by 4, then 1 by 2, then 1 by 3 by 4, and then finally 1. So this is subdivision. Similarly, this is also a subdivision, but note that this is not a subdivision of 0, 1, because here what is happening, we are taking the first point as a 0, then we are taking the point 1 by 2, and the next point, it should be greater than this, but we are taking the point, next point is 1 by 3. So it is not a subdivision. Now let us see what does it mean by refinement. If S and T are two subdivisions of AB, these two are subdivision, then T is called refinement of S if T can be obtained by adding some points in S. That is, in S, if we add some more points, then we get a new set, that is a larger set, that becomes the refinement. For example, let AB is equal to 0, 1 and S is equal to 0, 1 by 4, 1 by 2, and 1. And if we add one more point, that is 1 by 3 here, we are getting the T. So clearly S is subset of T. In this case, this T is called refinement of S. Now let us see the definition of component interval. If sigma is equal to x0, x1, xn is a subdivision of AB, then the closed intervals x0 to x1, x1 to x2, and so on, xn minus 1 to xn are called component intervals of sigma. For example, let us take 0, 1, and this is the subdivision of this. Then component interval will be 0 to 1 by 4, this is first, then 1 by 4 to 1 by 2 second, then I3 is 1 by 2 to 1. You can see with this diagram, these are the component intervals of sigma. Now let us see the definition of upper and lower sum. Let f is bounded function on closed and bounded interval AB and sigma is any subdivision of AB. Now let I1, I2 up to In are component intervals of sigma. Then in this case, UF sigma, what is this? This is called the upper sum of f corresponding to sigma, and it is defined by UF sigma is equal to summation k is equal to 1 to n mf ik into length of ik. That is the supreme value of f on I1 into length of I1 plus and so on. Supreme value of f on In into length of In. Similarly, the lower sum LF sigma, this is called lower sum of f and corresponding to sigma, and it is defined by LF sigma is equal to summation k is equal to 1 to n mf ik into length of ik. That is the infimum value of f m f on m f on I1 into length of I1 and so on. Similarly, up to infimum value of f on In into length of In. Note that this is remark MFIK. What this denote? This denote the supreme value of fx where x belongs to interval ik. Similarly, these two are self-explanatory. That is, small value of m is infimum value of f on ik where x belongs to ik, and modulus ik denote the length of component interval ik. Now let us see a remark. As infimum value of f on ik is always supreme value of f on ik, and this is true for all k, so this inequality hold, that is, we are multiplying by length of ik. And now if we take summation of both sides, we get, by definition, this will also hold, and by definition this become the lower sum and this become the upper sum. So here keep in this mind that this is very important, that lower sum of f on sigma is always less than upper sum of f on sigma. Now let us see quickly one example. Let fx is equal to x square defined on 0 to 1 interval, and let this is the subdivision of 0 1. We have to compute upper sum and lower sum. For this, component interval clearly will be I1 is 0 to 1 by 2, I2 is 1 by 2 to 3 by 4, and I3 is 3 by 4 to 1. So upper sum will be, by definition, supreme value of f on I1 into length of I1, supreme value of f on I2 into length of I2, supreme value of f on I3, length of I3. And when we put these values over here, because again we are considering fx is equal to x square, so supreme values will be at the end point. So 0 to 1 by 2. So supreme value on the first interval will be at 1 by 2. Accordingly, this value we have obtained, and length of I1 is 1 by 2 minus 0. Similarly, this value we got this, and length of I2 is this, and lastly this values. And when we calculate these values, and finally we obtain this value of upper Riemann sum. Similarly, we can find the lower Riemann sum by putting the values in this formula and just putting the values, all these values. Here we'll take the small values, infimum values, so it will be on the first point, that is on the 0 of the interval 1 by 2, because it is an increasing function. So this values when we put, and when we compute this, we finally get 5 by 64. So clearly here the lower sum is always less than or equal to the upper sum. This inequality holds. Now let us see the definition of upper integral and lower integral of f. Let f be bounded function on closed and bounded interval AB. So f is bounded function on this. We define the upper integral of f over AB denoted by a to b fx as upper integral of fx over ab is infimum of uf sigma, where sigma is subdivision. So keep in the mind this upper integral is always connected with upper sums, and we are taking the infimum, where infimum is taken over all subdivision of sigma over AB. Similarly, we define the lower integral of f over AB denoted by this notation as lower integral of f over AB is supremum of all f sigma, where sigma is subdivision. So again, keep in the mind a lower integral is connected with lower sums, and we take the supremum of all lower sums where sigma is any subdivision. We vary sigma as subdivisions and we take finally the supremum. So we get these values where supremum is taken over all subdivisions sigma of AB. Now let us take this example characteristic function. So let A belongs to R be any set, then the characteristic function chi A is defined as, we know this, its value at x is equal to 1 if x belongs to A, and its value is 0 if x does not belongs to A. So this is simply the definition of characteristic function. Now our task is give a function, example of a function f for which lower integral of f is less than upper integral of f, strictly less than. So let us take this chi b characteristic function of rational numbers in 0, 1. Then chi a x, according to this definition as I explained, it will be 1 if x belongs to 0, 1 and x is rational and its value is 0 otherwise. Now if sigma is any subdivision of 0, 1, then for any interval I belongs to 0, 1, if we take any interval whatever it may be, we have upper supremum of value of chi on x belongs to I will be mf xi, that will be 1, because in any interval I it will contain rational as well as irrational, so because of the rational contents its value will be 1. Similarly, small m xi, its value will be 0 because this interval will contain irrationals also. On an irrational its value is 0. So accordingly, if you find the upper sum, by definition of this, it will be 1 into sum of the length of interval, that is 1 minus 0, that will be 1, and the lower sum, that will be according to this definition, it will be 0 into 1 minus 0, that is 0. So all the upper sums value is equal to 1 and lower sums value is 0. So accordingly, lower integral will be supremum of all lower sums, that will be 0, and upper Riemann integral, it will be infimum of all upper sums, that will be 1. So clearly this lower Riemann integral is strictly less than the upper Riemann integral. Now let us see this last definition. If f is bounded function at a closed and bounded interval AB, then f is called Riemann integral on AB if the lower Riemann integral is equal to upper Riemann integral. If this happens, then in this case we define the lower Riemann integral is same as upper Riemann integral is integral of f over AB. And we denote by RAB the set of all function f which are Riemann integral on AB. Thank you very much. You can find the link of this lecture in the description box. Thank you very much.